AI is overwhelming, and this course is our humble effort to make it a little less intimidating and maybe have a little fun while we're at it. My name is Mamshat Manambat, and I'll be your instructor for this course. We start from the absolute basics of AI and work our way up to understanding what AI agents are. Along the way, we'll dissect OpenClaw, a popular open source AI agent that has gained a lot of interest recently, to see exactly what made it tick. But this isn't just another theory-only course. You'll get hands-on access to our lab environments where you practice building agents yourself, stress-free, without worrying about unexpected charges. We provide everything you need, from API keys to sandbox cloud environments, so you can focus purely on learning. Throughout this course, you will build 4 AI agents. I call them Zippy, Savvy, Meshy, and Cody. Pardon the choice of names. I thought they'd go well with the vibe. You'll see Zippy's journey from being a solo generic agent to becoming an orchestrator that manages a multi-agent setup of Savvy, a research agent, Meshy, a memory agent, and Cody, a coding agent. Here's how the course is structured. We start with fundamentals, the building blocks of AI. You'll learn what ChatGPT actually is, how large language models work, what tokens and tokenization mean, how temperature and sampling shape responses, and how to write effective prompts. From there, we move into architecture, how AI systems are assembled from parts. You'll learn what tools are and how to integrate them, building AI workflows, and understand the key distinction that most people miss. What separates a workflow from an agent? Then comes implementation, where you build real agents. You'll learn what an agent actually is, how agent memory works, planning and reasoning strategies, multi-agent systems, and error handling patterns. You'll also explore coding agents and the design patterns that Anthropic and Google use in production. We close with the OpenClaw case study, where we dissect a real open source AI agent. You'll walk through OpenClaw's architecture and tools, its agent loop, memory system testing strategies, monitoring and security. What's everyone's concern regarding OpenClaw's security challenges? Is it real? What caused it, etc. By the end, you'll know how to build, test, and deploy effective AI agents from scratch. And we're excited to release the first half of this course here on YouTube. So let us begin. Let's start with something you already know, ChatGPT. The name ChatGPT is actually 2 parts. Chat stands for the chat application, and GPT is the AI technology that powers it. GPT is the brain, and chat is the interface, the way you interact with the brain. GPT stands for Generative Pre-trained Transformer. Let's take it apart one word at a time in reverse order, because it's easier to understand that way. A transformer is a specific design for how an AI system processes language. It was invented in 2017 by researchers at Google. AI existed long before 2017. Many of us had already used some form of it: chatbots, spam filters, autocorrect, but it never felt truly intelligent. So what changed? At its core, AI works by predicting what comes next. Given some input, it makes its best guess about what follows. That basic idea hadn't changed. What changed was how well AI could do it, especially with language. In 2017, a team of researchers at Google published a paper called "Attention is All You Need." It introduced a new architecture called the transformer, and it quietly changed everything. You don't need to understand the technical details right now. What matters is this: before that, computers were bad at understanding language. After that, they got dramatically better. The key superpower of transformers is attention. The ability to look at all the words in a sentence at once and understand how they relate to each other. For example, consider this sentence: the dog chased its tail because it was bored. What does it refer to here? The dog or the tail? You instantly know it's the dog. Earlier AI systems struggled with this. Transformers handle it easily because they can pay attention to the relationships between all the words simultaneously. So that's what transformers are. Now let's look at the second word. The pre-trained part means GPT learned an enormous amount before it ever talked to a single user. Here's how that works. First, OpenAI, or the company training the model, collects billions of pages of text from books, websites, articles, code, and more. Imagine a library bigger than any library that has ever existed. That's roughly the scale of GPT's training data. GPT then read all of this text and learned patterns, not facts, not opinions, patterns. For example, after the capital of France is, the word Paris usually comes next. After once upon a time, a story usually follows. Technical questions tend to get structured answers, and casual greetings get casual responses. And the core of how GPT actually learns is by predicting the next word. During training, GPT was given billions of sentences with the last word hidden, and it had to guess what came next. Given the cat sat on the correct answer is mat. Given to be or not to, it's be. Given water boils at 100 degree, it's Celsius. It got it wrong a lot at first, but after seeing billions of examples, it got incredibly good at predicting what comes next. Not just simple sentences, but entire paragraphs across every topic imaginable. This is also why hallucinations happen. GPT isn't looking up facts, it's generating text that sounds like it should be correct based on patterns. And sometimes those patterns lead to astray. And finally, the generative part is the most straightforward. It means GPT creates new text rather than copying text from somewhere else. When you ask GPT a question, it doesn't search a database for a pre-written answer. It generates a brand new response, word by word, based on the patterns it learned during pre-training. GPT is a family of models that have gotten more capable over time. GPT-1 came out in 2018 and proved that the concept works. GPT-2 followed in 2019 and was good enough that OpenAI initially worried about misuse, and GPT-3 launched in 2020 and was a real breakthrough. It could write essays, code, and more. GPT 3.5 arrived in 2022 and powered the original ChatGPT launch. GPT-4 came in 2023 and was much more capable with the ability to understand images too. And GPT 4.0 launched in 2024, faster and with better voice and vision capabilities. Each version was bigger, more training data, more computing power, and better at predicting the next word. And GPT is just one family of LLMs. Other companies have built their own. Claude from Anthropic, Gemini from Google, and Llama from Meta, which is open source, meaning anyone can use it. They all share the same basic idea: transformer architecture, pre-trained on text, generating responses word by word. Now, it's important to note that the transformer architecture is used beyond language. Sora, which generates video, and various audio models also use transformers, but they're not LLMs because they don't work with language. The L in LLM specifically means language. Now, models like GPT-4o and Gemini blur this line. They handle texts and images and audio, so their core is still language model, but they've been expanded to understand other types of input. People still call them LLMs by convention. Now, let's dig into what makes LLMs large and why that matters. An LLM is what you get when you take the transformer architecture, scale it up with billions of parameters, and train it on massive text. Large refers to two things: large training data and a large number of parameters. To put this in perspective, all of English Wikipedia, every article ever written, is about 4 billion words. GPT-3 was trained on roughly 125 times that amount. Modern LLMs have gone further, still consuming text from books, websites, code repositories, scientific papers, and more. Now, if you read one book per week, it would take you 180,000 years to read what GPT-3 was trained on. Parameters are internal settings the model tunes during training to get better at predicting the next word. More parameters means more subtle control and better performance. But what does that actually mean? Think of it like learning to throw a basketball. Nobody consciously calculates the exact angle and force for every muscle in their arm. You throw, you miss, you adjust, you throw again. Eventually, your body just knows the right settings. Parameters work the same way, except with numbers instead of muscle memory. Each parameter is just a number, 0.87 or negative 2, 3. These numbers sit at the connections between neurons in the network and control how information flows through it. When the model is first created, all of these numbers are random. The model is essentially useless. It might predict that the cat sat on the ends with refrigerator. So how does it learn? The model is shown real text from books, websites, and articles, and asked to predict the next word. It guesses. Then it compares its guess to what actually came next in the text. If it was wrong, an algorithm nudges every parameter slightly in the direction that would have made the answer more correct. Then it does this again, and again, and again, billions of times. No human is writing these numbers or grading the answers. The training data itself is the teacher. It already contains correct natural language. The model just learns to mimic those patterns through repetition. And after billions of rounds, those random numbers have been shaped into an incredibly precise configuration that understands language. Again, you don't need to understand training in detail to build AI agents. That's the job of machine learning engineers who create these models. But knowing how it works helps you understand why LLMs behave the way they do and why they sometimes get things wrong. Now, to give you a sense of scale, look at how quickly these models grew. So GPT-2 had 1.5 billion parameters. GPT-3 jumped to 175 billion parameters. The jump from GPT-2 to GPT-3 was roughly 100 times more parameters. That's the difference between a model that could write passable text and one that could write convincing essays, translate languages, and write code. Now, bigger isn't always better, though. More parameters means more computing power, more cost, and slower responses. And sometimes a smaller, well-trained model is the better choice for a specific task. Now, LLMs are remarkably good at working with language. They can generate fluent, human-sounding text, summarize long documents, translate between languages, write code, follow instructions given in plain English, and shift their tone to match whatever you need: formal, casual, technical, playful. But they have real blind spots. So you ask an LLM to do math, and it might get it wrong because it's predicting words, not calculating numbers. You ask about something that happened last week, and it won't know. Its knowledge ends at whatever date it was last trained. If you ask it something that it doesn't know the answer to, instead of saying, "I'm not sure," it often makes up a confident sounding answer. And this is called hallucination, and it's one of the biggest challenges with LLMs. The biggest limitation, though, is the one that matters most for this course. On their own, LLMs can only produce text. They can't look up a database, send an email, book a meeting, or take any action in the real world. An LLM by itself is just a very impressive text generator. When we build Zippy later, we'll give him tools to overcome the limitations of a raw LLM. So give it tools, the ability to search, calculate, and take actions, and LLMs start to become an AI agent. Let us now see how developers use LLMs. When you use ChatGPT, you type in a text box and get a response back in the chat. When a developer builds with an LLM, they use an API, an application programming interface, a way for one program to talk to another. And here's what that looks like. Your application sends a request to the LLM provider, something like "summarize this text." The provider processes it through the model and sends a response back. It's a simple back and forth, request in, request out. Every AI agent is built using an API. The agent sends messages to the LLM, gets responses back, and decides what to do next. LLMs don't read text the way you do. You see words, and LLM sees tokens. A token is a chunk of text, sometimes a whole word, sometimes part of a word, sometimes just a single character. Before an LLM processes anything you type, it first breaks your text into these tokens. This process is called tokenization. Understanding tokens matter because they affect almost everything. how much a request costs, how much text you can send and receive, and why an LLM sometimes splits a word in a strange place. When you're building AI agents, tokens are the currency you're spending with every single interaction. So here's a concrete example. Take the sentence, "The tokenization process is fascinating." When tokenized, it breaks it into 6 tokens. The tokenization process is fascinating. Most of those words stayed whole. They're common enough to be their own token, but tokenization got split into 2, token and ization. So why did tokenization get split? Because the tokenizer learned that token and ization are common building blocks. By breaking words into reusable pieces, the LLM can handle words it's never seen before. So if it knows token and ization separately, it can also understand globalization, visualization, civilization, any word with that ending. The rarer the word, the more pieces it gets broken into. A word like anthropomorphization, I hope I got that right, because becomes 5 separate tokens. Not every word is one token. Common short words like the, is, and are each one token. They're extremely frequent in training data. Common longer words like computer and language also get their own single token because they appear often enough. Uncommon words like tokenization get split into 2 or 3 tokens, broken into known subpieces. Numbers vary by tokenizer and might be 1 or 2 tokens. Code tends to use more tokens because punctuation and keywords get split up, and non-English text typically uses more tokens per word because it was less represented in the training data. The pattern here is frequency. The more often a word or phrase appeared in the training data, the more likely it gets its own single token. Rare words, technical jargons, and non-English text get broken into smaller pieces, which means they cost more tokens and take slightly more effort for the model to process. Now, a rough rule of thumb, 1 token is roughly 4 characters of English text, or about 3/4 of a word. So a 1,000-word essay is roughly 1,300 to 1,500 tokens. Tokens aren't just a technical detail, they directly affect 3 things you'll care about when working with LLMs: cost, speed, and the context window. Starting with cost, LLM providers like OpenAI, Anthropic, and Google charge per token, both for what you send in and what you get back. More token means more money. To give you a real example, GPT-4o charges around $2.50 per million input tokens and $10 per million output tokens. A 500-word prompt costs fractions of a cent. But here's the thing. Output tokens are 4 times more expensive than input tokens. That's because input tokens are processed all at once in parallel, while output tokens are generated one at a time, each requiring a full pass through the model. That sequential generation is much more compute intensive. Now, this seems cheap for a single request, but an AI agent that makes hundreds of LLM calls per task can add up fast. Speed is the second factor. LLMs generate 1 token at a time. It's the next word prediction we covered earlier. Now, more tokens in the response means a longer wait. A 100 token response comes back much faster than a 2000 token response. And third, the context window. Every LLM has a maximum number of tokens it can handle at once. That's the context window. It includes both your input and the model's output. To give you a sense of how fast this has grown, GPT 3.5 in 2022 had a context window of about 4,000 tokens. GPT-4o in 2024 jumped to 128,000, and now in 2026, models like Claude Opus 4.6, GPT 5.5, and Gemini 2.5 all support up to 1 million tokens. That's roughly 750,000 words. Llama 4 Scout goes even further at 10 million tokens. So if your input and output together exceed the context window, the model can't process it. It's a hard limit, not a suggestion. We'll cover context windows in more depth in the upcoming lessons. One more thing worth knowing. Different LLMs use different tokenizers. The same sentence might be GPT-4 and 18 tokens in Llama 3. Each company trains their own tokenizer on their own data, so the exact splits vary. This means token counts are always approximate when comparing across models. Now, if you want to see this in action, OpenAI provides a free tool called the Tokenizer at platform.openai.com/tokenizer. You can paste any text and see exactly how it gets split into tokens. Try pasting a paragraph and notice which words stay whole and which get broken up. You've asked ChatGPT the same question twice and gotten different answers. Why? LLMs don't just pick the single most likely response every time. They calculate a probability for every possible completion, then sample from that distribution. Take a prompt like, write a one-sentence story about a robot. The model might give, a lonely robot discovered a forgotten garden, a 30% chance. In a world where emotions were outlawed, gets 15%, and thousands of other stories get smaller slices. The model rolls the dice. Responses with higher probability are more likely to win, but they don't always win. So now we know LLMs are choosing from a list of possibilities. But here's the natural question. How risky are those choices? Does the model always play it safe and pick the top response, or does it sometimes go out on a limb? That's exactly what temperature controls. Temperature is a number between 0 and 2 that you set when you call the model. Think of it like a dial that goes from strictly by the book to wildly creative. At temperature 0, the model always picks the most likely response. No randomness at all. Same input, same output every time. At 0.5 to 0.7, it mostly picks likely responses but occasionally surprises you. Crank it up past 1.0, and the model starts spreading its bets more evenly across all options, which gets creative and sometimes nonsensical. Here's a simple way to see this in action. Take our robot prompt and call the model 10 times at temperature 0, then 10 times at temperature 1.5. On the left, temperature 0, you get the same story every single run. A lonely robot discovered a forgotten garden again and again. On the right, temperature 1.5, every run is different. A robot building friends from junkyard parts, a robot learning to dream, a robot discovering emotions. Same prompt, completely different behavior, controlled by a single number. So when should you use each temperature? For data extraction and classification, use 0. You want the same answer every time. For code generation, 0 to 0.2. Code needs to be correct, not creative. General conversation, 0.5 to 0.7. Natural, but reliable. Creative writing, 0.8 to 1.2. You want variety and surprise. For AI agents, lower is generally better. You want reliable decisions, not creative ones. Temperature is set per API call. You control it, not the model. The context window is the LLM's working memory. It's the total amount of text the model can see at any given moment. Your input, the conversation history, and the model's own output all combined. Here's what it looks like in practice. Everything gets packed into one window. The system instructions, the conversation so far, your latest message, and whatever the model has generated. In a typical interaction, you might have 200 tokens of system instructions, 3,000 tokens of conversation history, 150 tokens for your latest message, and 500 tokens for the model's response so far. That's about 3,150 tokens total. If your model has a 128,000 token context window, you still have plenty of room. But everything inside the window, the model can see. Everything outside it doesn't exist to the model. This is a hard limit, not a suggestion. Different models have very different window sizes. GPT 3.5 had just 4,096 tokens, roughly 6 pages of text. GPT-4 doubled that to about 12 pages. GPT-4o expanded to 128,000 tokens, which is roughly 200 pages, about the length of a short novel. Claude 3.5 Sonnet goes up to 200,000 tokens, around 300 pages. And Gemini 1.5 Pro reaches 1 million tokens, about 1,500 pages. Larger context windows have been one of the biggest competitive battles between LLM providers. A bigger window means the model can process longer documents, remember more conversation history, and handle more complex tasks. So what happens when you hit the limit? When the conversation exceeds the context window, something has to go. Different systems handle this differently. The most common approach is truncation. The oldest messages get dropped. The model loses the beginning of the conversation and only sees the most recent messages. Another approach is summarization. The system asks the LLM to summarize older messages, then replaces the full history with that summary. This preserves key information in fewer tokens. And there's the sliding window approach. A fixed size window moves forward through the conversation, always keeping the most recent content. Let's see what truncation looks like in practice. Imagine you've been chatting with an assistant. Early on, you told it your name is Alex, that you prefer afternoon flights, and that you're vegetarian. But as the conversation grows past the context window, those early messages get dropped. The model can only see the most recent turns. It no longer knows your name or your preferences. This is why ChatGPT sometimes forgets things you told it earlier in a long conversation. It didn't actually forget. Those messages fell outside the context window. This brings up a critical distinction. The context window is not long-term memory. It's more like a whiteboard. Everything written on the whiteboard right now is the context window. When it fills up, you erase the oldest stuff. Long-term memory, by contrast, is like a notebook you can refer back to anytime. LLMs don't have this natively. Some products, like ChatGPT's memory feature, simulate long-term memory by storing key facts separately and injecting them into the context window on each request. But the underlying model still only sees what's in the window. For a simple chatbot, running out of context window just means the model forgets earlier conversation. Annoying, but not critical. For an AI agent, it's a much bigger deal. An agent might need to hold all of this in context at once. System instructions for how to behave, tool definitions for what tools are available, conversation history from the user, results returned from tool calls, and the agent's own intermediate reasoning. Here's a rough breakdown of how those tokens get used in a single turn. The system prompt takes about 2,000 tokens. Tool definitions for 10 tools eat up another 3,000. Add in conversation history, tool results, the agent's own reasoning, and space for generating a response. And you're already at around 23,000 tokens for just one turn. Each turn of the agent loop consumes context. A complex task with many tool calls can eat through the window fast. This is why context window management is a real engineering challenge when building agents, and why models with larger windows are so valuable. And bigger context windows aren't free. Remember, you pay per token. If you stuff 100,000 tokens into the context window, you're paying for all of those tokens on every single API call. An agent that makes 10 API calls with 50,000 tokens of context each time is paying for 500,000 input tokens, even if most of that context is the same conversation history repeated. This creates a direct tension. More context means better results, but higher cost. Managing this trade-off is one of the key skills in building production AI agents. You've learned that the context window is the model's working memory, everything it can see at once. Now the question is, what do you actually put in that window? Because what you give the model completely determines what you get back. Most people assume prompting is just about being specific. Give clear instructions, add some context, and you're done. That's what I thought too. But there's something strange going on under the hood. Here's an example that surprised me. These two instructions mean exactly the same thing. Don't use bullet points. Write in paragraphs only. Same meaning, but the second one works better, measurably, consistently better. Why? When the model reads, "Don't use bullet points," it first activates the bullet point pattern because that's the strongest signal word in the sentence, and then tries to suppress it. The suppression doesn't always win. You told it not to, but you also put the idea there. Prompting isn't just writing instructions. It's shaping which patterns in the model get activated. And once you understand that, the whole thing gets a lot more interesting. When you use the API, messages aren't just plain text. Every message has a role attached to it. There are 3 roles. The system role is for the developer. It sets the behavior, rules, and personality of the model. The user role is the actual question or request from the person using the app. And the assistant role is the model's response. Look at this messages array. The first item has role, system. That's the developer talking. The content says, "You are a personal assistant that helps manage schedules and tasks." That's the instruction that shapes every single reply. The second item has role, user. That's the person asking, "What's on my calendar today?" The system message is invisible to the user, but it's always there, always in context. In ChatGPT, OpenAI writes it for you. When you build your own app, you write it yourself. That's a big part of what makes the API more powerful than chatting. Let's make this concrete. The same question with 3 different prompts produces 3 completely different results. If you say, help me with my schedule, you get vague, generic advice about time management. Not very useful. If you say, list my meetings for today in bullet points with times, now the model knows the format you want and the information to include. Short, structured, useful. Go further. You are a personal assistant. The user has a busy day. Summarize their calendar, flag any conflicts, and suggest which meeting to reschedule if they're double booked. And now you get something specific, practical, and actionable. More context, more constraints, more useful output. Instead of summarize this, say summarize this in 3 bullet points for a technical audience. Every word you add to a prompt is a constraint, and constraints produce better output. This one is powerful. You can show the model exactly what you want by including an example in the prompt. This is called few-shot prompting, and the difference it makes is dramatic. Here's the same task, same question, with 2 different prompts. Without an example, 0 shot. There are 2 messages. The system message says, classify the sentiment as positive, negative, or neutral. The user message is, it took 2 hours to get our order. That's it. No example of what the answer should look like. And here's what the model produces. The sentiment of this review is negative. The customer experienced a long wait time, which suggests frustration and dissatisfaction with the service. You asked for a classification. You got an essay. The model had no idea you wanted one word. So it gave you what it thought was a thorough answer. Now with an example, few shot, this time there are 4 messages, same system message. But then before the real question, you insert 2 extra messages. A user message that says, the food was amazing, and an assistant message that says, positive. You wrote that assistant message yourself. It's not a real reply from the model. It's an example of what you want the reply to look like. Then comes the real question. It took 2 hours to get our order. And the output? 1 word. Exactly what you wanted. That one example did 2 things at once. It showed the model what kind of input to expect, and it showed what format to reply in. Without it, the model guesses at the format. With it, there's no guessing. You are a senior Python developer, produces different code than you are a beginner-friendly coding tutor. This isn't just a tone change. When you assign a role, you're activating a cluster of patterns from training, the vocabulary, the reasoning style, the priorities people in that role had when they wrote the text the model learned from. The system message is the natural place to put this. We already saw the don't use bullet points example. Here's the pattern more broadly. Left column, the negative version. Right column, the positive rewrite. Don't be verbose becomes be concise, 1 sentence per point. Avoid jargon becomes use simple words a high school student would understand. Every one of those rewrites is more reliable than the version it replaces. The model handles positive instructions more reliably. We'll see exactly why in section 4. Instead of plan my trip, try this. Step 1, check my calendar for the travel dates. Step 2, search for flights within my budget. Step 3, find hotels near my meeting location. Step 4, summarize the best options. This is called chain of thought prompting, guiding the model to reason through the problem step by step rather than jumping to an answer. Each step conditions the next one. When the model writes out step 1, that output becomes part of the context it uses to reason through step 2. The model builds toward a better final answer instead of guessing all at once. On the left, ChatGPT. You type one message, what's on my calendar today? And send it. Everything else is handled for you. On the right, the API. You build the full messages array yourself. The system message goes first. You are a personal assistant, be concise. Then the user message with the same question, same output, but now you're in control of every piece of input the model sees. Every concept from this section comes into play here. Your prompt consumes tokens from the context window. Temperature controls how the model samples its answer. And that entire messages array, system turn, user turns, assistant turns, all has to fit inside the context window you learned about last time. The techniques here will carry you through most of what you build. But there's a deeper layer. The research behind why these techniques work, why larger models can actually be worse at following negative instructions, how the order of information in a long prompt changes what the model pays attention to, and how a production agent like OpenClaw assembles its system prompt as a 19-section programmatically built file. That's what section 4 is for. For now, you have the foundation. You've spent the last few lessons learning what an LLM is, how tokens work, what temperature does, and how context windows limit attention. All theory. Now it's time to write code. By the end of this lesson, you'll have a Python program that sends a message to an LLM and prints the response. 7 lines of code. Every concept from the previous lessons will have a concrete home in that code. When you use ChatGPT, a lot happens invisibly. Your message gets packaged up, sent over the internet to a server, routed to the right model, and the model generates tokens one at a time. Those tokens stream back and appear as text on your screen. When you write code to call an LLM, you're doing the same thing, but you control every step. The communication happens through an API, an application programming interface. Think of it like a standardized order form. You fill it out correctly, send it in, and the kitchen makes your food. OpenAI provides an API so developers can use the same models that power ChatGPT in their own programs. To make API calls from Python, you use an SDK, a software development kit. It's a library that handles the formatting and communication for you, so you don't have to write raw HTTP requests. Without the SDK, talking to the API looks like this. You import urlib, manually build the HTTP request, set headers, encode JSON, decode the response. About 15 lines of boilerplate just to ask a question. With the SDK, 3 lines. Import OpenAI. Create a client, call chat completions, create. The SDK handles the HTTP, the headers, the JSON encoding, and error handling for you. Same result, far less noise. Let's walk through the code. Line 1. From OpenAI import OpenAI. This loads the SDK. Line 2. Client equals OpenAI with your API key. This creates your connection to the API. Set it up once at the top, then use it for every call. Lines 3 through 6. Client.chat.completions.create. You specify the model, GPT-4o, and a messages list with one user message. The result is stored in a variable called response. Last line, print response dot choices bracket 0 dot message dot content. Choices 0 is the first and usually only reply. Dot message dot content is the actual text string. That's it. 7 lines. Now let's add temperature. Remember lesson 5? Temperature controls how varied the responses are. Add temperature equals 0 to the API call and you get the same answer every time you run it. Change it to 1 and every run gives a different answer. This is the theory from lesson 5, running live in your terminal. Here's the complete picture. Every concept maps to something in the code. The LLM generating text, that's response.choices0.message.content. Tokens. Every word in your messages list is tokenized before being sent. Temperature, it's a parameter you set. Context window, everything in the messages list counts against it. Prompts, that's the content field in your message dictionary. Nothing in the code is magic. Every piece maps to something you already understand. All right, so that was a lot of theory. And now it's time to get our hands dirty. Use the link in the description below to go to the labs enrollment page. The labs for the first half of this course come free, so you don't have to pay anything. So you create a free account and sign up. And once in, you'll see the labs listed. Access them to get started. The lab environment already has the required API keys baked in, so you don't need to generate them from elsewhere. And these are valid for the duration of the lab. If you need keys to play around by yourself on your system, you can go to Code Keys page and you'll have access to the keys to access models from top providers like Anthropic, OpenAI, Google, DeepSeek, and you get a set number of tokens each month. If you're a paid subscriber to KodeKloud, these limits are much higher. There are also some sample projects there to get started with if you need some ideas. So go ahead and complete the lab, and I'll see you on the other side. You've seen the code. You know what every line does. Now it's time to run it yourself. In this lab, you'll take the exact program from the last lesson, the 7 lines that call an LLM, and run it with a real API key in a real terminal. No simulations. Your code, your credentials, a live model responding. Here's how it works. The environment is already set up. Python 3.11 is pre-installed. The virtual environment is active. You just need the SDK. Run pip install OpenAI and you're connected. Next, you'll create a file called hello_llm.py. Same code from the lesson. Import OpenAI, create a client with your API key, set the model to GPT-4o, send a user message, and print the response. You'll paste it in, save the file, and that's your script. Now run it. Python 3 hello_llm.py. And just like that, an LLM responds to your prompt in the terminal, not a chatbot interface, not someone else's app. Your code talking directly to the model. Here's where it gets interesting. Change the prompt to write a one-sentence story about a robot, then set temperature to 0 and run it twice. Same story, both times. A lonely robot discovered a forgotten garden. Word for word, identical. That's temperature 0. Deterministic, no randomness. Now change temperature to 1 and run it again. Different story, run it one more time. Different again. Same prompt, completely different output. This is lesson 5, running live in your terminal. Temperature isn't theory anymore. You can see it, control it, and predict what it does. That's it. You've written and run your first LLM program. Every concept from the last 7 lessons, tokens, temperature, prompts, context windows, now has a home in code you wrote. That's the foundation everything else in this course builds on. You've just made your first API call. You've seen the model generate text, follow instructions, and respond to different temperatures. It's impressive, and it's tempting to use it for everything. Don't. LLMs are powerful, but they're not the right tool for every job. Using one where regular code would work is like hiring a translator to read a stop sign. It'll work, but it's slow, expensive, and completely unnecessary. The key to building good AI applications, and eventually good AI agents, is knowing when to call the model and when to just write code. Every task you'll encounter falls into one of 2 categories. Deterministic tasks, where the same input always produces the same output. There's one correct answer and you can write exact rules to get it. Calculate a tip, sort a list, convert a date format, check if an email has an @ symbol. A few lines of code handle these perfectly, instantly, for free, and correctly every time. Then there are non-deterministic tasks, where the right answer depends on judgment, context, or interpretation. Summarize a legal document. Decide if a customer email sounds angry or confused. Write a professional reply to a complaint. These require understanding nuance, tone, and meaning. That's exactly what LLMs are built for. Here's the rule. If the answer is always the same for the same input, use code. If the answer requires judgment or language understanding, use an LLM. Let's walk through some real examples side by side. Calculate shipping cost based on weight. Code. It's a formula. Summarize a product review. LLM. Requires reading comprehension. Check if a password meets length requirements. Code. Len password greater than or equal to 8. Done. Decide if a review is positive or negative. LLM. Not bad for the price, needs judgment. Convert Celsius to Fahrenheit. Code. Exact formula. Extract a name and job title from an email. LLM. Names appear in unpredictable formats. Using an LLM when you don't need one has real costs. It's slower. An API call takes hundreds of milliseconds. A line of Python runs in microseconds. That's a 1,000-fold difference. It costs money. Every call uses tokens, and tokens aren't free. It can be wrong. Ask an LLM to compute 1247 times 83, and it might get it wrong. It's predicting tokens, not doing math. And it's unpredictable. Even at temperature 0, output can vary. Here's a real example. Say you're building a receipt generator. The math, subtotal, tax, total, that's regular code, deterministic. But the thank you note at the bottom, thanks for your purchase, in a different creative way each time, that's the LLM. Each tool does what it's best at. This idea comes back in a big way later in the course. When we build AI agents, they'll have tools, functions they can call to search a database, send an email, or run a calculation. Those tools are regular code. The LLM's job is to decide which tool to use and when, the judgment call. The tool itself handles the deterministic work. That's the pattern behind every good AI system. Let the LLM think. Let code execute. In the last lesson, you sent a single message to the API, one user, one question. That works. But in practice, the messages list is designed to carry a full conversation, and a conversation has more than one voice. The API supports three distinct roles: user, system, and assistant. Each message is labeled with one of these roles, and the model reads the full list in order before generating its reply. The user role is what you've already seen. It's the human side of the conversation. You send a question, the model answers. The system role is the developer's message to the model. The user never sees it. It's instructions set before the conversation begins. Think of it as the briefing you give a new employee before their first customer call. It sets the context for everything that follows. Here's a concrete example. Without a system message, you ask the model how to fix a bug, and you get a helpful, general, fairly verbose answer. Add a system message that says, "You are a senior engineer doing a code review, be direct and critical." And the same question gets a completely different response. The system message shifted which patterns the model draws on. What can you put in a system message? A persona. You are a friendly customer support agent. Constraints. Never discuss competitors. Format instructions. Always respond in bullet points. Background knowledge. The user is a paid subscriber. Every AI tool you've used has a system message running behind the scenes. ChatGPT, travel booking assistants, banking chatbots. They're not fundamentally different models. They're the same technology steered by different system messages. Now, the assistant role, this is the model's own previous replies added back into the conversation history. Why would you include the model's own messages? Because the model has no memory between calls. Every API call is stateless, and it starts completely fresh. The only memory it has is what you put in the messages list. So if you want a multi-turn conversation, you feed the history back in manually. You send the system message, the user's first question, the assistant's previous reply, and the user's follow-up. The model sees the full exchange. When it reads, "What's the population of that city?" it knows that city means Paris, because the previous turn is right there in the list. Without the assistant message in the history, the model would have no idea what that city refers to. This is how every chatbot maintains context, not with real memory, but by replaying the conversation on every single call. Three roles. System sets the behavior. User provides the input. Assistant maintains the history. Together, they give you full control over how the model responds and what it remembers. Welcome to this section on architecture. Now that you understand how LLMs work under the hood, it's time to ask the next question. How do we make them actually do things? On their own, LLMs can only generate text. But when you give them tools, the ability to search the web, query a database, or call an API, they become much more powerful. In this section, you'll learn how tool calling works and build your first tool calling application. Then we'll zoom out and look at the big picture. Not every AI system needs to be fully autonomous agent. Sometimes a simple, predictable workflow is the better choice. We'll explore the difference between AI workflows and AI agents, and just as importantly, when to use each one. By the end of this section, you'll have a clear mental model for how AI systems are structured, and you'll be ready to start building agents of your own. LLMs can only generate text. They can't check your calendar, send an email, or search the web. On their own, they're stuck inside their training data. Tools give LLMs the ability to do things. A tool is a function that the LLM can call to interact with the outside world. Without tools, an LLM can only answer from what it learned during training. Ask it, "What's on my calendar today?" and it has no idea. It can't access your calendar. But when you give it a tool, everything changes. Let's walk through what happens step by step. You ask, "What's on my calendar today?" The LLM reads that and realizes it needs real-time data. So instead of guessing, it decides to call a tool. It calls check calendar with today's date. The tool returns your events. The LLM responds, "You have two things today, team stand-up at 10 a.m. and a dentist appointment at 2 p.m. The LLM didn't know your schedule, it couldn't have. But it recognized it had a calendar tool available, called it, got back the raw data, and turned that into a useful response. The tool gave it the facts, and the LLM made them useful. A tool has three parts: name, what the tool is called; description, what the tool does, which the LLM reads to decide when to use it; and parameters, or what inputs the tool needs. The LLM reads your tool definitions and decides whether to call a tool and which one. This decision is part of the model's text generation, not a separate system. Here are the most common tool types. Search tools retrieve information, web search, database queries; calculation tools perform precise math; calculators, unit converters; API call tools interact with services; send email, create calendar events; file operation tools read or write files; code execution tools run Python or shell commands. A personal assistant agent might use all of these: search the web for restaurants, check your calendar for free slots, send an email to confirm a reservation, and save the confirmation as a file. Tools are just functions, nothing magical. They're regular functions that you write and expose to the LLM. The LLM decides when to call them, but your code actually executes them. You define the tools, the LLM decides which to call, your code runs the function, and the result goes back to the LLM. The LLM never runs the tools itself. It outputs a structured request, and your application handles execution. This is an important safety boundary. You control what the tools can actually do. Lesson 9. Tool integration. In the last lesson, we learned what tools are. Now let's look at how they work in practice through the tool use loop. When you give an LLM tools, it can respond with text, or it can output a specific tool call. If it asks for a tool, your code must execute the action and send the result back. This creates a loop. This pattern is often called function calling. Let's look at a scheduling example. If a user asks to schedule lunch, the LLM might first check the calendar, then search for a contact, finally create the event. The model can even handle multiple tool calls. If your request involves several pieces of information, the model makes those calls in sequence, or sometimes in parallel, before giving you a final answer. In code, it looks like this. You have a message list. If the LLM generates tool calls, your code iterates through them, executes each, and appends the result back to the messages for the LLM to process. This whole pattern is often called function calling. Remember, the LLM isn't running the code, it just outputs the intent in JSON. Your application is the middleman that actually does the work. Tool integration is what turns a simple text generator into a powerful agent capable of doing actual work. This is the foundation of everything we'll build next. Time to put this into practice. In this lab, you'll build a Python application where the language model decides when to call tools on your behalf. You'll define tool schemas, write handler functions, and wire up a tool call loop. The same pattern that powers every AI agent. Here's how the lab works. The environment is ready. Python 3.11, a virtual environment, and the OpenAI SDK are all pre-installed. Your working directory is /root/code. First, you'll create a file called tool_app.py. It starts with the basics: import OS and OpenAI, create a client using your API key and base URL from environment variables, set a system message, and initialize an empty messages list. Next, you'll define your first tool and check _calendar. The model reads the tool's name, description, and parameter schema to decide when to call it. You wrap it in a tools list following the JSON schema format: type function, a name, a description, and a parameters object with a required date string. Then you write the actual Python function, a mock that returns hard-coded calendar events, and a dispatcher called execute_tool that maps tool names to their Python functions. Now the interesting part, you add the user message, what's on my calendar today, and call the API with your tools list. The model doesn't answer directly. Instead, it returns finish reason tool _calls, telling your code execute this function first. You extract the tool name and arguments, run your local function, and append the result as a tool message. Then you call the API again. This time the model has the tool output and composes a final answer. Run it. Python 3 tool_app.py. The output mentions your calendar events, a team stand-up at 10 a.m. and a dentist appointment at 2 p.m. The model chose the right tool, your code executed it, and the model turned raw data into a natural language answer. That's the complete tool call loop, and it's the foundation every AI agent is built on. Now that you know how LLMs use tools, let's look at how developers combine LLM calls and tools into larger systems. These are called AI workflows, systems where LLMs and tools are orchestrated through predefined code paths. The key word is predefined. In a workflow, the developer decides the steps in advance. The LLM does the heavy lifting at each step, but the flow is controlled by your code. The simplest pattern: you break a task into sequential steps where each LLM call processes the output of the previous one. Say you want to draft an email and then review it. Step 1, the LLM writes the email. Step 2, a second LLM call reviews what the first one wrote and polishes it. You can add programmatic checks between steps, validate the output before passing it to the next call. In the routing pattern, you classify the input first, then send it to the right handler. A classifier LLM reads the user's message and decides which route to take. Is this a simple question, a scheduling request, or a complex travel planning task? This lets you use cheaper models for easy tasks and reserve expensive models for hard ones. Run independent subtasks at the same time instead of one after another. Sectioning splits the task into different parts that run simultaneously. For example, plan my Thursday kicks off checking the calendar, checking emails, and checking the weather, then combines them into a daily briefing. The other flavor is voting. Run the same task multiple times and take the consensus. Ask 3 models, is this content safe? And go with the majority answer. In this pattern, a central LLM dynamically decides what subtasks are needed and delegates them to worker LLMs. The orchestrator reads the input, breaks it into pieces, farms them out, and then combines the results. Unlike parallelization, the subtasks aren't predefined. The orchestrator figures out what work is needed based on the input. This pattern uses 2 LLMs working together. One generates a response, the other evaluates it and gives feedback. The generator takes that feedback, improves its output, and the cycle repeats until the quality is good enough. This is useful when quality matters more than speed, like translating nuanced text or writing production code. In every pattern above, the code controls the flow. The developer decides which steps happen, in what order, what gets passed between them, and when to stop. The LLM is powerful, but it's operating within a structure you designed. This is what makes workflows predictable and debuggable. Lesson 11. Workflows versus agents. In the last lesson, you saw how developers combine LLM calls and tools into workflows. In a workflow, you define the flow, which steps happen, in what order, when to stop. You draw the map before the journey starts. But what if you can't draw the map in advance? A customer emails saying their account was charged twice. To investigate, you might check payment history, but what you find there determines the next step. Maybe you need to look at their subscription, maybe cross-reference a refund policy, maybe check for an existing support ticket. You don't know until you're already inside the problem. Or a user asks, find me a cheap flight to London next weekend. There isn't one. Do you stop, check the following weekend, try a nearby airport? The right move depends on what you just discovered. Or a developer asks an AI, why is this test failing? Answering that might mean reading files, running commands, checking logs. No 2 bugs follow the same path. In all these cases, the steps can't be predefined. Someone or something needs to decide what to do next on the fly. That's what we're looking at now. Both workflows and agents are agentic systems. They combine LLMs with tools to accomplish tasks. The difference is who controls the flow. In a workflow, you, the developer, decide the steps in advance. The LLM executes each step, but the sequence, branching, and logic are defined in your code. Your code decides, step 1, call LLM to classify input. Step 2, based on classification, call LLM to generate response. Step 3, call LLM to translate response. The LLM is powerful at each step, but it doesn't choose what to do next. Your code does. In an agent, the LLM decides what to do next. It looks at the current situation, picks a tool, uses the result to decide the next action, and keeps going until the task is done. The LLM decides, I need to check the calendar, calls calendar tool. There's a conflict, let me find alternatives, calls search tool. I found an option that works, generates final response. The developer provides the tools and guardrails. The LLM decides how to use them. Let's put these side by side to see the differences clearly. In a workflow, the developer defines the steps, execution is predictable, and you know exactly how many LLM calls you'll make. In an agent, the LLM decides the steps, execution is dynamic, and the number of calls varies depending on the task. It's not always a clean binary. Most real systems fall somewhere on a spectrum. On the far left, you have a pure workflow where every step is predefined. Move right, and you start giving the LLM more control. First, it picks a path, routing, then it decides what subtasks to create, orchestrator. And at the far right, you have a fully autonomous agent running in a loop with full control. Moving right on this spectrum means giving the LLM more control. More control means more flexibility, but also more cost, more latency, and harder debugging. Ask yourself, can I draw a flowchart of every possible path before running it? Yes, it's a workflow. No, it's an agent. Lesson 12. When to use each. You now know the difference between workflows and agents, but knowing the difference doesn't tell you which one to build. That's a practical question that comes up every time you start a new project. The wrong choice has real consequences. It doesn't just make your code harder to write, it makes it more expensive to run, harder to debug, and more likely to break. There's a principle that cuts through the noise. Find the simplest solution possible and only increase complexity when needed. Most tasks don't need an agent. A workflow or even a single LLM call is often enough. Before building anything, ask yourself the simplest question first. Can a single LLM call handle this? If yes, just do that. If you need multiple calls working in sequence, you want a workflow. And if the LLM needs to decide its own steps based on what it discovers along the way, that's when you consider an agent. Each step up the ladder adds cost, latency, and complexity. Only climb when the simpler approach genuinely can't do the job. Workflows shine when the problem is well understood. If you already know the steps, even if the inputs change, a workflow is almost always the better choice. Think about email classification and response, daily briefing generation, data extraction, translation chains. These tasks have a clear shape. You can describe the steps before you run them. The steps don't change based on what the LLM finds. The flow is predictable. Every input takes the same path. Agents earn their complexity when the task is genuinely open-ended, when the right path depends on what the LLM discovers along the way. Think about trip planning, personal assistant tasks, complex scheduling, coding assistance. These tasks don't have a fixed shape. The steps emerge as the work happens. The LLM needs flexibility. It needs to adapt based on what it finds. Different inputs take different paths. The LLM decides what to do next. Getting it wrong has a real cost. Using an agent when a workflow would suffice means you're paying more per request. You're waiting longer for responses. You're spending more time debugging paths that change every run. You've also given the LLM room to go off track on a task that didn't need that freedom. On the other hand, using a workflow when an agent is needed creates a brittle system. It breaks on inputs you didn't anticipate. It can't handle edge cases. It needs constant updating every time requirements change slightly. If you're weighing both options, run through these 4 questions. They'll point you in the right direction. First, can I define all possible paths in advance? If yes, choose workflow. If no, choose agent. Second, does the LLM need to make decisions about what to do next? If yes, choose agent. If no, choose workflow. Third, is this a well-defined, repeatable task? If yes, choose workflow. If no, choose agent. Fourth, does cost need to be strictly controlled? If yes, choose workflow, or at least add guardrails to the agent. Answer these 4 questions and you'll know which tool to build. And here's the thing, the best systems often combine both. A workflow handles the predictable parts. An agent handles the parts that need flexibility. You don't have to choose just one. Start simple. Use a workflow. Add an agent when the workflow can't handle what you're throwing at it. Mix and match. The principle is the same. Start with what works and only add complexity when you need it. Here's what you need to remember. Workflows follow a path you design. Agents decide their own path. Most tasks need a workflow. Some tasks need an agent. The wrong choice costs you money, time, and debugging headaches. Use the checklist. Start simple and only increase complexity when the simpler approach genuinely can't do the job. You've now learned about agents, workflows, tools, and patterns. You know how they work and when to use them. Next lesson, we're going to put it all together. I hope you're enjoying the course and the hands-on lab so far. If you're finding this learning experience valuable, please consider supporting us by subscribing to KodeKloud. For just a couple of $100 a year, you get full access to this course plus over 200 other courses covering everything from the fundamentals of computer science, DevOps to MLOps, cloud computing, and AI. Every course is hands-on and comes with built-in lab access. If you're not sure where to start, our curated learning paths guide you step by step through the specific career tracks, whether that's DevOps engineer, cloud architect, or AI engineer, so you'll always know what to learn next. You'll also get access to playgrounds. These are sandboxed cloud environments across all three major platforms: AWS, Azure, and Google Cloud. Plus, Code Keys gives you API keys to experiment with AI models hands-on. Every lab comes with an AI assistant built right in. So if you get stuck, you get immediate context-aware help without leaving the exercise. And our AI tutor takes it further with personalized learning that adapts to your pace and fills in your knowledge gaps. If you need to review or revise, the KodeKloud Notes app gives you access to all the notes across all of our courses in one place, your go-to reference for quick lookups and exam prep. And our job simulation platform, KodeKloud Engineer, drops you into a realistic work environment with daily tasks, so you're not just learning concepts, you're practicing what the job actually feels like. Programs like 100 Days of DevOps, 100 Days of Cloud, and the upcoming 100 Days of AI give you structured learning paths that keep you consistent and accountable. You're never learning alone either. Join our active Discord community to connect with thousands of other learners and drop into weekly office hours to get your questions answered live by our instructors. We have cohorts that are running to help you crack certification exam together with thousands of others who are along the same journey. And with the KodeKloud mobile app, you can keep learning on the go, whether you're commuting, on a break, or just away from your desk. So all of that for a fraction of the cost of a traditional college degree or an online boot camp, because we believe learning shouldn't cost you a fortune.